All right. Last time we talked about the anatomy of waves, crests, troughs, wavelength, frequency, period, all that, wave speed. Now we can actually take this and start applying it to sound. Um, most sounds are waves produced by vibrations of matter. In stringed instruments, sound is produced by the vibrating strings. So if you slow down a vibrating string in slow motion, you'll actually see it make a sine wave. In some wind instruments, sounds produced by a vibrating reed. So the reed is what you would put sort of up against your mouth, and then as you blow air into it, the vibrating reed is where you get your sound from. Of course, your voice. What you hear come out of someone's mouth is just the result of air vibrating inside their vocal cords. So their vocal cords are vibrating. In all these cases, the original vibration stimulates the vibration of something larger. So if you're playing piano, your string is going to vibrate the soundboard of the piano. In an instrument like a flute or something, it's going to vibrate the air column. Or let's see, gosh, what's a reed instrument? No band people crucify me. A clarinet, I think, has a reed. So if you blow into that, the reed's going to vibrate the air column inside. And then of course the your vocal cords vibrate, and that could also that will also vibrate the air column inside your throat and mouth. Now, vibrating material sends a disturbance through the surrounding medium, which is air, in the form of longitudinal waves. Okay, these are a little bit different. We'll talk about them shortly. So what we hear when these vibrations come and hit our ear, we describe this in terms of its frequency, and we use the word pitch. So low pitch sounds have a low frequency or a long wavelength. So they look like that. And then high pitched sounds will have a high frequency. So there's a lot of vibration going on. So high pitched sounds would be more like that. So low pitch, low notes on the piano, long wavelength, high notes on the piano, short, squiggly wavelength. So these would be your bass notes. And then the higher would be more like your treble. So sound waves with frequencies below 20 hertz are infrasonic. This is like how elephants communicate. They actually communicate with infrasonic sound. And with frequencies above 20,000 hertz, these are called ultrasonic. And turns out humans generally can't hear sounds out in these ranges. So extremely low frequency, below 20 hertz, or extremely high frequency, above 20,000 hertz. You all probably can hear these at some stores. I know if you go up to Boone and you go to Harris Teeter, they actually have this high-pitched like beeping noise to keep high school kids from hanging out in the parking lot. When I was younger, I could hear it, and now I can't really hear it anymore. I don't know if they got rid of it or if I'm just old enough to not hear it. But that's actually one application of this ultrasonic sound, where you can actually use it as a deterrent to keep younger people from hanging out in your parking lot. So in liquids and solids, the atoms are relatively close together. We know that. And in this situation, when you have these propagating sounds, these atoms really close together respond quickly to one another's motions, and they transmit energy with little loss. So it turns out that sound travels about 4 times faster in water than in air. Okay, so a liquid compared to a gas. and then about 15 times faster in still than in air. So if you want to get your sound even faster, have it transfer through a solid versus a gas. Now, relative to solids and liquids, air is a poor conductor of sound. So it turns out the thing that we use to communicate with each other the most, air, the thing that transfers our sound, is actually one of the worst things you can transfer sound through. And that, of course, is just because there's less atoms in a gas than there are in a liquid or a solid. So that makes sense as to why sound will not travel in a vacuum, because if you get past a solid, liquid, or a gas and there's just nothing there, there's no medium, there's nothing to compress and expand and pass that along. Okay, let's talk about specifically sound in air. So if we think about a single sound pulse, so like a single clap of your hands, this produces a non-periodic disturbance. So it produces a wave pulse that travels outwards in all directions. Now, what happens is when you clap your hands, you push all those molecules between your hands together, and that is called a compression. So the compression travels and propagates through the atmosphere. So you're compressing these atoms, and they want to get out from between your hands, so that you squeeze them out from between your hands. Okay. Now, if you continued clapping, your hands would come together, push the air out, and that's the compression. They bump into other molecules. When you open your hands again after the first clap, air is going to rush back into that gap that you just made. Okay. Now, when you make this gap, you sort of make a little vacuum there, and then the air is going to come back in. So this returning air is called rarefaction, and that's hard for me to say. So you've got compression and rarefaction, and both of these, even though one of them, the air molecules go away from you, and then the other one, they sort of come back, it creates this chain reaction that propagates outward. So that's what's going on in this picture here. So when you open the door in this room, you're compressing. Ooh, I need a different color. Here we go. When you open the door in this room, you're compressing all these air molecules. They bump into each other, and then you can sort of see the curtain blow. And then when you close the door, okay, so this door is closing. When you close the door, you sort of make a vacuum behind the door, right here. You make this vacuum behind the door, and then all the molecules sort of move over. So these sort of move over to fill the space, fill the space, fill the space, fill the space. So even though they're sort of moving back toward the door, you see the effect propagate outward. Okay, so that's why the arrow points to the right in both of these, even though we have molecules going in both directions. It's the effect that gets transferred. So I should probably write that. The effect propagates to the right. Okay, so don't get confused by why the arrows point in the same direction, even though molecules are sort of moving in two different directions in these cases. Let's think about this again in terms of more periodic sound, so it's not just a single pulse. So let's consider the sound waves from a tuning fork. Oh, this should say a tuning fork. There we go. And this tuning fork is going to form sound waves in a tube. So when the prong of the tuning fork moves toward the tube, it causes a compression. Okay, so these things here, they are vibrating back and forth. So when the one on the right moves toward the tube, it causes this compression. When the prong finishes moving toward the tube, it starts moving back. It causes a rarefaction. Okay, because it's going to move back, it's going to create a little vacuum, and then it's sort of going to suck those molecules back. So here we have compressions followed by these refractions, and then you just keep getting this back and forth effect, and you can see that the wave is going to propagate through the tube. Now, as the source vibrates, this motion becomes periodic. So we get a periodic series of compressions and rarefactions. And anytime you listen to the radio in your car, this is exactly what's happening in your speaker. So your speaker is usually just like a paper cone here, sort of like this area. If you ever had the speaker out of your car, it's usually just a really thin material. So this paper cone actually vibrates in rhythm with an electrical signal. So the frequency of the vibrating source and the frequency of the wave it produces are the same. So essentially, whatever signal you're inputting into your speaker, it's got to have some sort of wave motion, right? That's going to cause your speaker to move back and forth. So whatever the frequency of the electrical signal is, it's going to be the same frequency coming out of the speaker. And those air molecules next to the vibrating cone, they start vibrating. And then that gets propagated through the air molecules in your car. Eventually it hits your eardrum, and then it sets your eardrum into vibration. Now, the weird thing about nature is that your brain can sense the vibration of your eardrum, because your eardrum will turn its mechanical vibration into electrical signals, and then your brain can interpret those electrical signals. Something to note is that while all this is happening, the speed of sound only depends on wind conditions, temperature, and humidity. It does not depend on the loudness or the frequency of the sound. So a low sound will not travel faster than a high-pitched sound. They travel the same speed. If you scream louder, it's not going to get there faster. Even if you whisper, it's not going to get somewhere slower. The only thing that changes how fast sound travels is actually the medium that it travels in. So all sounds travel in the same medium, same speed. If you wanted to change the speed of your sound wave, you can't change the sound wave. You have to change what it is traveling through. So it turns out that the speed of sound in dry air is roughly 330 meters per second. Now, if we increase the water vapor in the air, this will actually increase the speed a little bit, just because there's more molecules to bump around. If we increase the temperature, this also increases the speed, because that makes the molecules actually move faster. So you have your sound coming through, moving molecules, and if they're already moving fast, then you get a slight speed increase in your sound. So let's think about this in terms of a question. So what is the approximate distance of a thunderstorm when you note a 3-second delay between the flash of lightning and the sound of thunder? Let's see, I'm going to get rid of this A and make the sentence a little bit easier to read. Okay. So we have something happen, we have 3 seconds, and then we hear the thunder. So we have flash, 3 seconds, thunder. Well, this sounds just like a regular old distance equals velocity times time approach. So we can start with an assumption. We'll assume that the speed of sound in this air, because it's got water and it's got water vapor, is a little bit faster, so 340 meters per second. Okay. Now, we can start with our original definition of velocity, distance over time. We can rearrange it just like I've already done. So we know that if we want the distance, well, that's just velocity times time. So we know the velocity of sound through moist air. We know how long the time it took to get from the lightning flash to us. So we can multiply these things, and it turns out this storm is about 1,020 meters or 1.02 kilometers away. So now that we've talked about speed and the wave speed and speed of sound through air, what that means for us is that wave motion of all kinds actually possesses energy, because you have to have something moving, it's an energy transfer. And this is true not just for sound, but also for electromagnetic waves. So obviously we get energy from the sun in the form of electromagnetic waves. Turns out light waves like that, electromagnetic waves, these are relatively high energy. Sound waves, on the other hand, are really small energy. So yeah, just speaking like this is really, really low energy compared to the energy we're getting from a light bulb in the room. Now, when you do speak, though, that energy dissipates to thermal energy while it travels in the air. So higher frequency waves are actually transformed into this internal energy more rapidly than lower frequency waves. So that's why lower frequency waves are used if you need to have a sound travel a long distance. So like boat horns, they need to travel a long distance, so they're going to be a lower frequency, or like foghorns in San Francisco. Everyone knows sort of what a foghorn sounds like, and they're always a low frequency. That's because you can sort of maximize your distance with that low frequency. Okay, let's think about another question here. So we have an oceanic depth sounding vessel, so a boat that's measuring the depth of the ocean. And it's surveying the ocean floor with ultrasonic sound that travels 1,530 meters per second in seawater. Okay, so that's really fast. How deep is the water if the time delay of an echo from the ocean floor is 2 seconds? Okay, so we all know what an echo is. We have a situation where you have a boat. You have sound going down and coming back up. Yeah, okay. Now here's the trick to this question. We want to know the depth of the water. We want to know the depth of the water, but you have to remember that we're listening for the echo to come back after it's bounced off the sea floor. So that means we have to divide the time it takes by 2 seconds, because this is the time it takes to get down there and come back. If we use this time here, we get the depth of the ocean twice, right? Because we get it once for the sound going down, we get it again for the sound going back up. So we need to be careful and remember to divide this by 2. Okay. So in that case, we know that the depth, or the distance that the sound travels, okay, cutting that time in half would be 1 second. So when we do the simple multiplication here of the speed of sound in seawater and how long it takes, we get 1,530 meters as the depth. Okay, so let's look at this other question here. While sitting on the dock of the bay, Otis notices incoming waves with distance of 1.8 meters between crests. The incoming crests lap against the pier pilings at a rate of 1 every 2 seconds. Okay, so we want to find the frequency of the waves and find the wave speed. Well, we know how to calculate frequency. We've done this before. So that's just the oscillations per time. The problem says that in the second sentence, the incoming crest lap against the pier pilings at a rate of 1 every 2 seconds. So that's what we have here, 1 every 2 seconds, which is 0.5 hertz. We can use that frequency to actually calculate the wave speed. So we have a distance of 1.8 meters between crests. Okay, so we multiply that by the frequency we just calculated. It turns out we get a wave speed of almost 1 meters per second. So it's about 0.9. Okay, now we just talked about an echo there, and we sort of have an intuition of what an echo is, but let's actually look at this in a little more detail. So an echo is literally just the reflection of sound. So the fraction of energy carried by the reflected sound wave can be large if the surface is rigid and smooth, or small if the surface is soft and irregular. So that's why if you hang up a bunch of curtains in your home, you get less echo and the room sounds a little more dead. Whereas if you've ever moved into like a new apartment where there's no curtains or pictures or anything, you sort of get some reverb if you like walk into a completely empty room and shout or something. So that's what's going on, is if you have these soft irregular surfaces, they will absorb a lot of that echo and you won't get it back. You can see here, it looks like these are probably some pretty smooth surfaces because you're getting a lot of echo. And it turns out whatever angle a sound comes in at is also going to be the angle that it leaves at. So there's a bit of geometry here in constructing speakers and sound systems and things like that, because you have to take into account some of the geometry as sound gets propagated from the speaker. Of course, now all that energy, if it doesn't get reflected, all that energy does get absorbed by whatever your soft or smooth surface is. And now if a sound undergoes multiple reflections, so if these are bouncing all over this room here, and it keeps going after the source is stopped, that's actually called a reverberation. So that's if you're in a very smooth, maybe, I don't know, metallic room or something, you'll get a lot of reverb in there. So you'll keep hearing that sound even after the source is stopped. Now, if reflective surfaces are too absorbent, you'll have a very quiet sounding room. So this would be really great in a church. You want your church to sort of be quiet. Depending, I mean, there's some, like the big historic churches that were sort of set up to where the minister would be up front and everyone could hear him because there is a lot of echo and sound travel as well. But I mean, in modern day churches where you have a sound system, sometimes it's better to have a newer church built such that there is a lot of dead atmosphere in the church in regards to sound, because it keeps the echo down, keeps the reverb down. It's a little harder or a little easier to hear. On the other side of this, reflection of sound in a room will make it sound lively and full. So there's a reason, like in coffee shops, you know, if there's not a lot of stuff hanging on the walls, you'll get a lot of reverb, and coffee shops will sound very lively. A coffee shop that I sometimes go to here in Pasadena, It's a brick building, so it's got brick walls, exposed brick, and then it also has a concrete floor. And sometimes it gets too loud and I have to leave just because there's so many surfaces. And it's a big rectangular room. So there's not like little rooms that will sort of dampen the sound or extra walls or anything. So, something to keep in mind if you're thinking about opening a coffee shop or something where there's going to be a lot of sound. You'll want to pay more attention to what kind of walls you have, what the shape of the room is, that kind of thing. In case of like an auditorium, you need to sort of balance between the two. You want a little reverb so the room doesn't sound dead, but then you also you don't want the sound to just keep reverbing on and on and on. So you do need some absorption. And this whole balancing act, in the study of sound and sound engineering, is called acoustics. So if you're a musician, you've ever spent time in a recording booth in a sound studio, a lot of engineering, a lot of thinking about this has went on in regards to making sure that you get the right mix for those people that are going to record albums. Now, what's really weird as sound propagates is that the direction of sound can actually bend depending on the properties of the air at the time that the sound is happening. So when sound waves continue through a medium and bend, this is actually called refraction. Okay, so make sure you note that this is not rarefaction. So we have a lot of different words floating around. That's why it's hard for me to say these words, because they're so similar and they're floating around in the same conversation. So we have refraction, and that's when sound wave will actually bend. So sound waves bend when parts of the wavefronts travel at different speeds. Okay, we'll go through these bullet points and we'll apply it to this picture over here. So parts of sound waves traveling at different speeds might occur in uneven winds or when sound is traveling through uneven temperatures. But the key word here in both of these is uneven winds or uneven temperatures. You have to have some sort of abnormality in the medium. So refraction of sound is caused by differences in the speed of sound. Makes sense because we have uneven properties in the atmosphere. Sound refraction explains why you can clearly hear conversations over a campfire across a lake at night. I don't know if you've ever noticed, but if you're ever camping around a lake, maybe in a campground where there's lots of people, when everything's quiet and it's nighttime and the air's cooling down, you can actually hear across the lake fairly well. So what's going on if we look at example A here? The bottom part of the sound wave is in warm air near the ground. Warm air makes the sound travel faster. So what you get is fast traveling sound or faster traveling sound in the warm air near the surface. And then as you move up, you're moving into colder air. So it starts traveling slower and slower the higher you get. So essentially, over time, you get a sound that sort of curves up. Now, if the surface is cool, but the air above is a little warmer, you can see this sometimes in places like Salt Lake City, where there's a temperature inversion, where you get some warm air that sort of makes a lid over the Salt Lake Valley. And what happens is you've got this warm air up here, so sound can travel a little faster. But then as you move closer and closer to the surface, the sound will travel slower and slower, and then you sort of get this downward turning sound. Now we can use this to our advantage, and we have been for quite some time, and lots of animals have been doing this as well. But the refraction of sound occurs underwater. Makes sense because the density of the water changes at different heights. Also, the temperature changes at different heights, so you get sort of double varying things here. Because there's thermal gradients and layers of water at different temperatures, The refraction of sound leaves gaps or blind spots in the water. And it turns out this is where submarines hide. So if this was not a physical phenomenon happening, if sound did not refract in the ocean, submarines would be so much easier to find. But because sound gets bent, and the main approach to finding submarines is sonar, there are pockets where submarines can hide, and this sonar signals will actually get sort of bent away from them. Of course, doctors, physicians, they use reflections and refractions of sound, specifically ultrasonic waves. So if you go get an ultrasound, basically they're just using sound waves to see inside your body. And what's nice about this is that it's a harmless view inside your body. There's no need to use x-rays. There's no need to use MRIs. It's literally just a sound wave, nothing to it. So there's no harm in using ultrasound to see inside someone's body because it's just sound waves. And of course, we've been using ultrasounds for a while, but this is also how dolphins and bats communicate. They actually make pretty high pitched sounds, and they use the reflection of those sounds back to understand densities and sizes of objects in the water. Well, bats don't do that in the water, they do that in the air, but obviously dolphins do that in the water. So there's some applications of sound and a basic overview of how sound works. After this, we will move into light. So we've talked about anatomy of waves. We've applied that to sound. Now we're just going to finish up and talk about light and how light propagates and exactly what light is. So until then, if you have any questions, please let me know.